After the early Llandovery anoxic event had ended, the oxygen returned to the shelfal sea. The sea level was still rising fast, so that the earlier glacial flow barriers eventually were flooded. Large-scale water circulation systems began to operate, mixing the ocean waters and eliminating the anoxic water masses across the shelf. The hemipelagic muds that were now deposited were healthy and green, containing only negligible amounts of organic matter. They represent the bulk of the Tanisoft Formation. Up to 500 meters of Tanisoft shales formed in Morzuk. In the Kufra Basin, the unit is markedly thinner and usually no more than 100 meters thick. Why so little in Kufra? Kufra lies on the proximal part of the North African shelf, close to the early Silurian sandy coastal zone. By mid-Llandovery times, the coastline began to shift northwestwards and quickly reached the Kufra Basin, the end of hemipelagic Tanisoft muds and the beginning of deltaic sandstone deposition, the Akakos sands. The Morzuk Basin was overrun by these sands only later, allowing extra time to pile up more mud here. At first glance, it's hard to believe that the coastline began to shift seawards at all during the mid-Llandovery, because the post-glacial sea level rise at that point in time was still in full swing. Rising sea level, yes, but outweighed by far by a huge pile of sand parked in the North African river mouths that was now actively pushed by more sand into the sea. Throughout Silurian times, numerous rivers transported enormous amounts of sand from the Gondwanan hinterland towards the North African coast. The early Llandovery transgression still managed to trap these sands in the river mouths, where they backstepped unwillingly onto the coast. By the middle Llandovery, however, so much sand had been accumulated in the coastal belt that huge deltaic fans began to form in Kufra, shedding the sediment into the sea. Layer by layer, the delta system built out onto the shelf. A prograding deltaic front developed that must have stretched over more than 2,000 kilometers. There's no deltaic system on Earth today that even comes close to these dimensions. On a scaled-down level, however, the present-day largest delta of the world may give us an idea of how such a long deltaic coastline may have functioned. The Ganges Delta in Bangladesh and India is 350 kilometers long and is fed by 240 individual rivers, the largest of them being the Ganges and the Brahmaputra. The general architecture of the Silurian Akakos Delta may have not been very different to the Ganges system. Numerous rivers draining the huge Gondwanan hinterland may have joined forces and formed the deltaic Akakos front. The general northwestward movement of the Akakos Delta was occasionally interrupted by third-order sea level cycles that pushed the shoreline slightly back towards the land. In the Ghat area, a series of 3 to 4 shallowing upward sedimentary packages formed, separated by pronounced flooding surfaces. A sedimentary architecture interpreted as parasequence in the sequence stratigraphic model. In general, Akakos times in the Morzuk Basin must have been rather peaceful for the inhabitants of the Silurian Sea. Abundant trace fossils speak of luxurious times with plenty of oxygen available at the sea bottom. The king of all traces is undoubtedly Cruziana.
Well, Cruziana is the burrow of a trilobite. And it's made by the legs burrowing strangely, not away from under the body, but towards the midline. So actually the sediment was carried together under the body. This means the animal did not want to get burrowed for protection, but it wanted to loosen the sediment and filtrate the sediment and process under the dorsal shield, which was just on top of it. And here we can see the details of the claw formula. They have 5 round claws, and if they are larger, we can see that there is a notch in the middle of each claw.
The trilobites were not alone. The sand must have been also full of worms, leaving behind an amazing labyrinth of simple-structured arthrophycus tunnels. In some Akakos beds, Cruziana and Arthrophycus traces are intensely interwoven. Scenes of a fierce hunt? Not at all. In reality, the two animals hardly got to meet each other.
Well, this is 2 generations of burrows. First you have here the trilobites coming from very shallow above, and then the deeper burrowing worms here, they came up with sedimentation and crossed it, and then they searched out the old trilobite burrows, and if they could, went along them.
Akakos life must have been good, with probably one exception. Climbing up the Akakos escarpment in Wadi Tanazuft, the cliff in the lower part exposes a mysterious unit with strangely patterned surfaces. The imprints appear to originate from gas bubbles that got trapped in biomats. Usually there's little room for biomats in healthy ecosystems because they make a perfect dinner for many sea creatures. The wide occurrence of these mats indicates that the ecosystem might have turned sick for a few million years. In fact, it was a second anoxic event that had struck, an event that terrorized the North African Arabian shelf for a short while during the late Llandovery to early Wenlock. Offshore the sandy delta zone in the Caledonian Basin, a stinking black mud was deposited during this event, the so-called Upper Hot Shale, a unit that's absent in the Morzuk and Kufra basins because the sandy delta sediments had already overrun them at that time. The Akakos Delta slowly worked its way through to western Algeria. But before it could reach Morocco, the early Devonian arrived. The sea had suddenly had enough and withdrew. The end of the Akakos deposition. It happened at a time when sea levels dropped worldwide. But there was also something else that kept Libya quite busy during those days. Part of the Morzuk started moving upwards. We're still not quite sure why these movements took place. Certainly, Libya was not involved in any nearby plate collisions at that time. According to some specialists, the tectonic stress could have originated from Morocco. The Armorica terrane that includes parts of present-day France seems to have broken away from northwest Africa during the early Devonian. The tectonic stress that resulted from this divorce may have travelled thousands of kilometres into the southern Libya intraplate, triggering the uplift, as it did in the western Algerian Regan Basin and the Mauritanian Malian Tau Deni Basin. In the Morzuk Basin, uplift and oistatic sea level fall joined forces. Hungry as they were, they took a huge bite into the ground and removed part of the Carcass sands that had just been deposited. In other areas, they wanted more, cutting away all of the Tanisoft, including the precious Silurian source rock. In the northeastern Morzuk, erosion took out even the uppermost Cambro-Ordovician layers. The erosional event is known in North Africa as the Caledonian Unconformity.
The most prominent tectonic events that shaped Libya are the Caledonian.
For the Caledonian, really had uplifted the center of Mizuka Basin. And so I think the Caledonian had provided a new paleo-highs.
The most obvious place to see the Caledonian Unconformity is the northern Gussa. It's the eastern edge of Mizuka Basin. But the Akrakus pinches out towards the south, towards central Gussa, between Tartarat sandstone and Tanisoft shale. And later, even farther south, Tanisoft shale pinches out, and the Cambro-Ordovician is directly overlain by Tartar, by lower Devonian strata then.
The Unconformity's early Devonian age matches quite well with that of the real Caledonian orogeny in Laurasha, which inspired the geological pioneers of North Africa to choose the same name. But in fact, there's no genetic link between the two compressional activities. Gondwana is far away from anything at this time. The Caledonian erosion was just one of various phases when the thoroughly deposited sand grains were ripped out of their beds and set alive once again. Taconic, Caledonian, Hercynian, Austrian, Alpine. Attacks on the quartz particles were numerous.
These sands were redeposited, in fact were redeposited on margin, on depositors, where the depositor is in the outcrop.
Some grains that found their final resting place today in the Mesozoic Nubian sandstone have been recycled 3 times since their first deposition in the Cambro-Ordovician. The North African Shelf, a cannibalistic system. The Caledonian uplift changed the structural architecture of Libya. Before the Caledonian, the early Paleozoic substrate of Libya is thought to have been dominated by north-northwest, south-southeast trending structures. Ridges and troughs controlled the facies and thickness distribution in southern Libya on a scale of hundreds of kilometers. These trends are often hard to detect within individual concessions, but operate more on a basin-wide scale.
We see some evidence that there was onlap onto particular paleoarches, some of the big broad north-south paleoarches, but essentially it was one series of continuous linked sag basins that ran across the whole of the North Gondwanan margin.
Jebel Gargaf was part of a north-northwest striking high during Silurian, and this is the high you can see at Moide. At Moide, along the track down to Chad, there is Silurian directly on basement.
The vast majority of strata in the Morzuk and Kufra basins dip only gently towards the respective basin centers. The dip angle is very low. Often it's really nearly flat-lying.
But even this flat-lying strata evidently had undergone structural differentiations. To find out that these structural differentiations can be mapped, can be shown on maps, was interesting. And what we had on the preliminary geological maps showed basins and areas between basins. But what I found out already in the first field campaign was that a basin was not necessarily a basin all the time. There were highs and there were lows during different times and changing during the times.
Part of the early Paleozoic pre-Caledonian action is captured in stone at the eastern margin of the Mizuka Basin.
At northern Doric-Gussa you see a very strong unconformity of Ordovician strata with an angle of about 15 or even more degree overlying steeply dipping pre-Ordovician, Cambrian or infra-Cambrian, we don't know. The uplift happened probably in, as early as Cambrian or early Ordovician. It's one of those very old structural elements. So this is the old structural setup, and it changed towards the end of Silurian. Towards the end of the Silurian, we suddenly got a totally different structural setup. The northwest direction became common, and we got sedimentation of Devonian and Carboniferous in troughs, and later in Permian Triassic time in troughs which had a different direction of strike and different centers as well.
So the early Devonian Caledonian uplift marked an important change in the tectonic regime of southern Libya. As the area was partly uplifted and oistatic sea level fell, the Gondwanan feeding rivers quickly invaded the former marine deltaic zone. The Tadrat sands arrived. Wide bundles of shallow river channels covered the low-lying areas of southern Libya. Every day, the braided systems kept pushing their sandbars further downstream. The movement is preserved in the monotonously dipping tabular crossbeds. The Tadrat rivers were rather unreliable. The channels frequently became clogged and alternative routes were established. New bars formed and soon they'd been eroded again. The water discharge varied from extreme floods to weak trickles. And there was no space for fines here. The strong currents swept the muds out of the braided river basin, leaving behind a nicely cleaned Tadrat sand. The crossbeds piled up and today form towering walls in the Caucasus Mountains, a national park of stunning beauty. Textbook-like. The lower Tadrat is massive, fluvial strata everywhere. But then the sea must have remembered the good times it once had in southern Libya. It wanted to come back. Several attempts to reclaim the territory were only short-lived, and each time the river sands managed to strike back. Several cycles developed in the Upper Tadrat with alternating marine and fluvial facies. But the final winner was the sea. Marine sands, siltstones and shales of the early Devonian Unkaza formation mark the end of the fluvial Tadrat times. The Tadrat surely makes a nice potential reservoir. There's only one little problem. And that is that the Tadrat today is completely absent in the central and northern parts of the Mizuka Basin. Eroded by a Middle Devonian uplift event underneath the so-called Mid-Iphalian Unconformity. Following the early Devonian Caledonian tilting, the Tadrat and Unkaza were deposited on top of the erosional surface. During the Middle Devonian, another intraplate uplift event struck. Short-lived, but very effective. The central and northern parts of the Mizuka were pushed up and the Unkaza and Tadrat taken out. The Mid-Iphalian even eroded through the Caledonian Unconformity and helped to remove more of the Akakus and Tanisoft. When the Middle Devonian erosional event was over, the sea came back. It's often surprising to see how innovative and exciting nature can be. And on the other extreme, also how boring sometimes. Throughout the Middle Devonian to late Carboniferous, nature in southern Libya had only one thing in stock: monotonous oistatic sea level oscillations. Sands and shales deposited from shore face to storm wave base. The sand-dominated parts of the cycles during the sea level lows, the shale-dominated packages usually during the sea level highs. Only during rare occasions the acidic clastics paused for a short while and carbonates formed. Time went by. Formation names changed. Awainat Wanin during the Middle to Late Devonian, Mara, Acid Jafar, and Dimbaba during the Carboniferous. The depositional pattern, however, stayed the same. At the northwestern Mizuka margin, the Middle Devonian to Carboniferous sandstones form prominent ridges on a huge desert plain. Old ridges around Al Awainat younger ridges along the roads towards Ubari. Very easily accessible from the asphalt road connecting the two towns. A paradise for the lazy geologist who hates to leave his air-conditioned car for too long. The basinward-dipping Paleozoic strata have created a superb quest to morphology. The hard Tadrat and Akakas sandstones from the large ridge of the Akakas Mountains. The soft Tanisoft shales, a wide wadi that's also home to the town of Ghat. The Cambro-Ordovician sandstones in the extreme west make another gentle ridge. There are some nice sands in the Upper Paleozoic. Could they be alternatives to the traditional Ordovician reservoirs?
What I think is particularly interesting is there are other possibilities in southern Libya that still require quite a lot of work and a lot of exploration to understand and to recognise whether or not they are working petroleum systems. Two that are of particular interest are the Devonian system. We already have some hydrocarbons encountered within the Devonian, but generally rather small amounts. But there's no reason why the Devonian and indeed some of the later Silurian sands shouldn't work in that region.
In one of the areas we have what we call the sea structure, we have, yes. The main reservoir is in Devonian, what we call the BDS, Basal Devonian sandstone. And I'm sure that in some areas it should be the main reservoir within Mizuka Basin.
You have to consider the Carboniferous too, because the Carboniferous also is producing, capable of production in Achan area. But most important thing is that the Devonian, hot shale, Franian is not present in Mizuka Basin. Now what you have to see that your source rock have to be Silurian.
In most parts of the Murzuc, the Devonian and Carboniferous sands are separated from the Silurian source rock by the Tanisoft shales, a very effective seal. The only way up for the hydrocarbons is along faults.
So you really depend on the faults, and you wanted the faults to play as conduits for migration of oil to go to the Devonian on top of that thick Silurian section. At the same time, you have to be careful about the side seals. You need another strong side seal actually to have the oil migrated to your reservoir.
We can use Achan field, was discovered by ESSO in 1959. I think it is an example and it is a school to understand if we really want to explore the Devonian and the Carboniferous.
And as far as we can determine at the moment, it requires that we have some juxtaposition of the Devonian reservoirs against one of the other carrier beds in order to charge the Devonian structures. And that's one of the main reasons why relatively few of them that have been tested have worked successfully so far.
Towards the end of the Carboniferous, Earth prepared for a change. The continents once again came together for one of their rare reunions. The legendary supercontinent of Pangaea ruled the world. Southern Libya stayed out of any trouble. The nearest collisional zone was in northwest Africa, where Gondwana crashed into North America. The most intense deformation of the so-called Hercynian orogeny was concentrated over the northwest coast of Morocco and Mauritania. The compressive stress, once again, was transmitted far inside the plate interior. But when it arrived in southern Libya, there wasn't that much left of it. While the Hercynian created spectacular angular unconformities in the Ghadames Basin of northwest Libya, the effects in Murzuc and Kufra appear to be more on the subtle side. But in reality, they were an important step on the basin's way to adulthood.
Certainly in broad regional terms, one of the primary effects of the Hercynian unconformity was to accentuate both north-south and east-west trending arches, so that really at that stage in the geological history we began to differentiate and separate the individual basins as we see them today. So the separation of the Mizuka Basin from the Kufra Basin, the Mizuka Basin from towards the north, the Gadames Basin, certainly appears to become prominent in the Hercynian period, and then has been periodically reactivated throughout the rest of the geological history. And again, the Alpine deformation has been the final phase in that history, if you like, in determining the uplift of some of these arches separating the main basins.
Prior to the Hercynian collision, the northwest African shelf appears to have been actively dragged down, accumulating several kilometers of sediment. Soon the Silurian source rock was buried under a big pile of strata. The organic matter matured and hydrocarbons were generated that migrated into pre-Hercynian traps. When the continental collision happened, some of these traps were damaged, and a lot of these pre-Hercynian generated hydrocarbons escaped to the surface and were lost. Complications that mostly affected parts of Morocco and Algeria. And what about southern Libya?
From the modelling we've done, we don't believe there was a significant amount of generation pre-Hercynian in this area at least.
The most obvious effect of the Hercynian in southern Libya was that it had lifted the area out of the sea. The sea had to go, and rivers and lakes were the new masters of the Murzuc and Kufra. And they liked it so much that they dumped their red sands and muds here for more than 150 million years, until the late Cretaceous.